A robotic spacecraft sends its final signal and then vanishes into nothingness. These lost voyages are the ghost stories of the space age, untold tales of ambition and mystery. By the end of this journey, you will know the true stories behind more than 24 silent probes and the profound lessons they left drifting in the void. We will uncover why a billion-dollar mission can disappear just days from its goal, and what strange shadow one spacecraft cast in its final moments before going dark. What does it truly mean to send a piece of ourselves into the great unknown, never to hear from it again? That first golden age of spaceflight was built on a foundation of sheer nerve. Nations were in a race, not just to the moon, but to prove a new kind of technological supremacy. They built these early robotic probes with slide rules and vacuum tubes, sending them on journeys of millions of miles with less computing power than a modern car key. Every launch was a gamble. You could have the most brilliant scientists on Earth, but a single faulty wire, a tiny valve that failed to open, or a misaligned gyroscope could turn a billion-dollar dream into space junk in an instant. The Soviet Lunar program, for instance, saw multiple spacecraft simply vanish during launch or on their way to the moon. One might suffer a guidance failure, spinning off endlessly into a solar orbit we can never track. Another would have its rocket explode on the launch pad, a fiery end before the journey even began. NASA faced its own ghosts with the early Pioneer probes, some of which fell silent due to power failures or crippling radiation. These were not just lost machines, they were lost time, lost hope, and lost data. The silence from space was a brutal teacher. It forced engineers to think about redundancy, to build backup systems for the backup systems. It made them confront the sheer volume of nothingness between worlds, where a signal could grow faint and a battery could freeze solid. Out of this painful learning curve emerged a new generation of more resilient robots. But one mission in particular would cement the fear of the void into the consciousness of every space agency. It was the first probe ever designed to leave Earth's orbit for another planet, and it simply vanished without a trace. The cosmos was not done teaching its harsh lessons. Just months after Sputnik's beeping signal shocked the world, America's answer sat ready on the launch pad. The Vanguard TV-3 was a small, polished sphere no bigger than a grapefruit, a symbol of hope and scientific ambition. Millions watched on live television as the countdown reached zero. The rocket ignited, began to rise, and then, just 2 seconds into its flight, it simply collapsed back onto the pad in a massive fireball. The tiny satellite was thrown clear, its transmitters still weakly beeping from the wreckage. This was not a mystery in the depths of space, but a very public, humiliating failure. A single, simple flaw had caused the disaster. A fuel line had ruptured, starving the engine and causing a catastrophic loss of thrust. The entire rocket was a victim of its own rushed development, a project pushed forward under immense political pressure to catch up in the space race. Newspapers across the globe mocked the failure with cruel nicknames like Kaputnik and Flopnik. For the engineers who had poured their hearts into the project, it was a devastating, very public funeral for a machine that never even touched the void. Yet that very public loss became a foundational lesson. It proved that ambition alone was not enough. Every component, every valve, every wire had to be perfect. The perseverance born from that flaming wreckage led directly to a new culture of obsessive testing and quality control. The Vanguard program itself would eventually succeed, but its first, very loud failure set the stage for all the quieter, more profound disappearances to come. The next ghost would not die so publicly. It would slip away in the profound silence between worlds, leaving behind a mystery that would haunt scientists for decades. A tiny error, a miscalculation lasting less than a second, sent the first spacecraft ever aimed at the moon on a journey into eternal silence. Lunar 1 was a polished metal sphere bristling with antennas, a symbol of Soviet ambition to strike the lunar surface. In January 1959, it raced away from Earth on a perfect trajectory, but its final rocket burn lasted a fraction of a moment too long. That minuscule overcalculation, a slight nudge of excessive speed, meant the probe did not fall towards the moon but flew right past it, missing by nearly 4,000 miles. In the control room, the intended celebration of impact turned to stunned silence as their creation sailed gracefully into the void. The mission, conceived as a hammer blow, became a feather on the solar wind. Lunar 1 had failed completely in its goal, yet it achieved a monumental, accidental first. It became the first human-made object to escape the Earth-Moon system and enter an orbit around our Sun, a ghost ship of the inner solar system. For a brief period, it transmitted data on the previously unknown solar wind. A silver lining of science gleaned from failure. Then, its batteries drained and radio signals faded forever. It remains out there still, a silent artificial planet on a million-year journey, a permanent monument to a tiny human mistake. This was a new kind of loss, not a fiery explosion or a sudden systems failure, but a clean, precise miss dictated by mathematics. It proved that reaching another world required a level of navigational exactness never before attempted. An error you could barely measure on Earth became an unbridgeable gulf in space. The void was not just a place of random catastrophe, but a realm where perfection was the only acceptable standard. This concept of the navigational ghost, a probe lost to a simple calculation error, would return to haunt space agencies again, but next time the destination would be infinitely farther away, and the mystery would deepen beyond all expectation. Some ghosts never make it past the front door. For the Mariner 8 spacecraft, its entire mission to map the red planet ended not in the void between worlds, but in the dark waters of the Atlantic Ocean. Just 365 seconds after a perfect launch in May 1971, the Centaur rocket stage began to tumble. Its guidance computer had failed, overwhelmed by a single faulty component. Instead of soaring towards Mars, the probe and its rocket fell back through the atmosphere, a brief, brilliant fireball signaling the end of a billion-dollar dream. Mariner 8 was a twin built alongside the identical Mariner 9. They were designed to work as a team, one to map the planet from a high orbit while the other studied specific targets. With its twin shattered in the ocean, Mariner 9 was left to shoulder the entire scientific burden alone. This loss was a brutal lesson in what engineers call a single point of failure. One tiny, flawed part in a labyrinth of thousands could bring the entire intricate machine crashing down. It proved that the most dangerous part of any voyage is often the very beginning. The journey of millions of miles could be lost in the first few minutes. Yet, from this very public disaster came an incredible story of resilience. Mariner 9 arrived at Mars later that year, only to find the entire planet shrouded in a global dust storm, the worst in centuries. With its original mapping mission impossible, the team adapted. They waited patiently for months until the storm cleared, and then Mariner 9 performed flawlessly, becoming the first spacecraft to orbit another planet and returning a breathtaking trove of data that rewrote our understanding of Mars. The ghost of its lost twin had forced a flexibility that turned potential failure into legendary success. But what happens when a spacecraft does everything right, survives the launch, and travels for months, only to vanish just as it reaches its goal? The silence that followed Phobos-2's last transmission was not the quiet of empty space, but a roar of unanswered questions. After a flawless journey to Mars, the sophisticated Soviet spacecraft had successfully entered orbit and begun its study of the red planet and its strange, potato-shaped moon. It was on the cusp of its most daring maneuver, a descent to within just 50 meters of Phobos to release 2 landers, when it spoke for the final time. The signal did not fade, it was severed. One moment, Phobos-2 was a functioning scientific outpost. The next, it was just another ghost. The final fragments of data it sent back only deepened the mystery. The last image, a long, thin, and unmistakable shadow cast on the surface of Mars itself, did not match any known feature of the spacecraft or its orbit. It was an anomaly, a phantom shape that should not have been there. Official reports concluded that a probable computer failure, perhaps initiated by a mistaken command from an exhausted ground controller, had caused the probe to tumble, losing power as its solar panels spun away from the sun. Yet, the strange final photograph fueled decades of speculation, from secret military experiments to encounters with the utterly unknown. The truth is likely more tragic, a simple, human error cascading through a complex machine at the worst possible moment. The loss of Phobos-2 was more than the death of a single probe. It was the effective end of the Soviet Union's ambitious planetary exploration program. The immense resources and national prestige invested in the mission evaporated into the Martian silence, leaving a scientific void that would take other nations years to fill. How could a spacecraft so close to a monumental success simply cease to be? Its story is a stark reminder that in the final frontier, the greatest dangers can be the smallest mistakes. But if a failure at Mars feels remote, what about a ghost that vanishes from the very edge of our solar system? Their final goodbyes were not explosions, but a slow, quiet fading. The twin Pioneer probes 10 and 11 became ghosts not in an instant, but over decades of dedicated service. Launched in the early 1970s, these rugged explorers were the trailblazers, the first to brave the treacherous asteroid belt and send back breathtaking close-up views of Jupiter and Saturn. They fundamentally reshaped our understanding of the outer solar system, revealing turbulent, storm-racked giants where before we had only seen faint dots of light. For years, they faithfully phoned home, but as they raced farther into the void, their nuclear power sources decayed and their signals grew fainter. Each transmission required more effort to hear, until the day arrived when the listening antennas on Earth could no longer pick their whisper out from the cosmic background noise. The final contact with Pioneer 11 came in 1995, while Pioneer 10, the more tenacious of the pair, held on until 2003. For the engineers who had nurtured these missions for over 30 years, it was like saying goodbye to an old friend, listening until the very last moment the voice could be heard. Yet during their long journeys, these spacecraft presented scientists with a profound puzzle. They were experiencing a tiny but consistent deceleration, a drag that could not be explained by known physics. For years, this Pioneer anomaly hinted at the possibility of new laws governing the cosmos, a mystery born from the silence of deep space. It was eventually traced back to something far more ordinary, though no less fascinating: the subtle push of heat radiating from the spacecraft's own systems. Now, these silent ambassadors continue their endless voyages. They carry with them golden plaques, engraved messages to any hypothetical future finders, depicting humanity and our location in the galaxy. They are on trajectories that will take them past distant stars over millions of years, eternal ghost ships sailing into the great dark. This slow, graceful fade into silence stands in stark contrast to the next kind of loss, a category defined not by a dwindling power supply, but by a single, shattering instant. The Mars observer carried the weight of a generation's curiosity on its shoulders. This billion-dollar flagship mission was poised to become the first American orbiter at Mars in over 17 years, a technological marvel designed to conduct a comprehensive global survey. Its sophisticated instruments would peer through the ruddy haze to map the entire surface, analyze the thin atmosphere, and search for clues to the planet's watery past. Then, just 3 days from its triumphant orbital insertion, the spacecraft fell silent. The scheduled call from millions of miles away never came. Engineers sent frantic commands into the void, listening for any whisper of a response, but the silence was absolute. One of the most expensive planetary missions ever conceived had vanished on the eve of its greatest achievement. The leading theory points to a single, catastrophic moment. As the spacecraft prepared for its Mars orbit insertion burn, it needed to pressurize its propulsion system. Investigators believe a tiny valve may have opened too quickly, sending a surge of pressurized nitrogen gas into the fuel line. The shock of this pressure pulse could have ruptured the line, allowing hypergolic fuel and oxidizer to mix uncontrollably. The result would have been either a violent explosion that tore the spacecraft apart or a crippling spin that sent it tumbling, its antennas pointing uselessly away from Earth. An alternative explanation is equally haunting. A latent electrical short, perhaps caused by the intense vibration of launch months earlier, might have finally triggered at the worst possible time. This could have forced the spacecraft into a protective safe mode, but a flaw in its programming may have prevented it from ever waking up. Like a sleeper who will not rouse, the Mars observer would have drifted past its target, a ghost ship sailing silently by the red planet it was meant to study. The profound tragedy of the loss was the total lack of data. With the final telemetry stream cut off, investigators were left with only theories, piecing together the spacecraft's last moments from ground tests and simulations. How does an agency recover from such a devastating, enigmatic blow? The loss forced NASA to abandon its philosophy of building single, expensive flagships. In its place arose the faster, better, cheaper approach, which championed smaller, more focused missions. Out of the ashes of the Mars Observer disaster came a new fleet of explorers, like the Pathfinder lander and the Global Surveyor orbiter, which would ultimately fulfill the lost mission's goals. This pivot proved that even the most profound silence could teach a valuable lesson, a lesson about redundancy, resilience, and the need to never put all your scientific eggs in one fragile interstellar basket. The silence that greeted the Beagle 2 lander was a quiet, personal heartbreak. On Christmas Day 2003, this tiny British probe, no larger than a bicycle wheel, detached perfectly from its mothership, the Mars Express orbiter, and began its descent through the thin Martian atmosphere. Cheers and anticipation filled the control room, but they were waiting for a signal that would never come. The lander, named for the ship that carried Charles Darwin, simply vanished. For over a decade, its fate was one of the solar system's most frustrating puzzles. Led by the charismatic and determined Professor Colin Pillinger, the Beagle 2 was a triumph of ambition on a budget. It carried a sophisticated laboratory packed into its small frame, including a robotic mole designed to burrow into the Martian soil and retrieve samples for analysis, a direct search for the chemistry of life. Its complete radio silence after landing day led to years of painful speculation. Did it burn up in the atmosphere? Did it crash into a canyon wall? Or did it land safely, only to be doomed by something far more subtle? The answer finally came from the sharp eyes of another robot, high above the red planet. In 2015, NASA Mars Reconnaissance Orbiter captured an image that solved the mystery. There, on the surface of Mars, was the Beagle 2. It had landed successfully, right on target. the spacecraft had survived the harrowing entry and landing perfectly intact. But the images revealed a devastating truth. Some of its 4 solar panels, which unfolded like the petals of a flower, had failed to deploy completely. One stubborn panel likely remained closed, physically blocking the lander's communications antenna. Beagle 2 was alive and well on the surface, but it was mute, trapped in its own shell, unable to tell anyone of its success. This discovery transformed the story from one of total failure into a heartbreaking tale of a near-perfect landing. It had accomplished 99% of its mission, only to be defeated by a single, tiny mechanism. How could a hinge, a latch, or a small motor, something so simple, silence a mission designed to answer one of humanity's biggest questions? The ghost of Beagle 2 is a stark lesson in the absolute reliance on communication and the unforgiving nature of deployment sequences. Every single action in space must happen in a perfect chain, and one broken link, no matter how small, can render a multi-million-dollar dream permanently silent, a functional machine waiting forever for a command it can no longer receive. A ghost can haunt a space program twice. Years after Beagle 2 fell silent, another European lander aimed for the Red Planet. The Schiaparelli entry, descent, and landing demonstrator was a critical test, a rehearsal for a future rover mission that would search for life. For 6 minutes, it plunged through the thin Martian atmosphere, its heat shield glowing, a parachute deploying to slow its furious descent. Data streamed back to Earth, a steady heartbeat of information. And then, as before, the signal vanished. This time, however, the silence was not absolute. The data it sent in its final moments provided a chillingly precise autopsy report. The lander's internal navigation system, its inertial measurement unit, became saturated with data during the violent parachute deployment. This sensor overload created a catastrophic miscalculation. For a single, fatal second, the computer believed it had already landed, even though it was still floating nearly 4 kilometers above the surface. Acting on this false belief, it jettisoned its protective shell and parachute far too early. Its braking thrusters, fired for only 3 seconds before the computer, convinced the job was done, shut them down. The result was a long, silent, and utterly unstoppable free fall. Schiaparelli did not land on Mars. It struck the planet at over 300 kilometers per hour. The scar of its impact, a dark patch surrounded by ejecta, was later photographed from orbit, a permanent grave marker. The failure was not in the hardware, but in the logic, a subtle software flaw that simulations had failed to catch. How do you prepare for a mistake the machine itself decides to make? This was a ghost born from a paradox, a lander that died because its own brain was tricked into thinking it had already survived. The forensic record from its death plunge became a priceless, if painful, lesson in designing for the unpredictable chaos of a real planetary landing. It proved that every sensor needs a backup and every calculation needs a second opinion, a principle that would be tested to its absolute limit on the next and most daring landing attempt of all. Sometimes the most ambitious ghosts are the smallest. While the world watched the Mars polar lander in December 1999, 2 tiny stowaways were about to embark on an even more daring mission. Named Amundsen and Scott after the legendary polar explorers, the Deep Space 2 penetrators were not designed to land. They were built to crash. Each one was a bullet-shaped probe, no larger than a basketball, clinging to the sides of their doomed mothership. As the lander began its own fatal descent, it released these 2 darts. They were supposed to slam into the Martian soil near the South Pole at nearly 200 meters per second, a violent impact meant to drive them deep into the ground. Their goal was revolutionary, to test whether a network of cheap, rugged probes could be scattered across Mars to analyze the soil and subsurface water ice. They were packed with miniaturized sensors and a communication system tough enough, in theory, to survive the high G-force of a planetary impact. The silence that followed was absolute. Not a single beep was ever heard from Amundsen or Scott. With the Mars polar lander also lost, the entire mission became a double mystery, a single event that erased 3 separate spacecraft from existence. Without any telemetry from the lander or the penetrators, investigators were left in the dark. The most probable explanation is also the most brutal. The penetrators simply shattered on impact. The Martian surface at the pole might have been far harder than the models predicted, more like concrete than soft dust. Their delicate internal electronics, despite being ruggedized, could have been instantly pulverized. Alternatively, their small antennas, designed to pop up after impact, might have been damaged or blocked by soil, trapping their data inside a silent, buried tomb. The Deep Space 2 mission was a high-risk gamble on a new kind of space exploration, one that accepted failure as a price for innovation. Its total silence is a stark reminder of the alien and unforgiving nature of another world's surface. What does it take to survive a high-velocity impact on an alien world? The answer, it seems, is a level of toughness we are still learning to build. A ghost can be born from fire just as easily as from silence. The Contour spacecraft did not fade away, it erupted. In July 2002, this pioneering explorer was poised to embark on an unprecedented tour of comets. Its mission to swoop past the ancient, icy nuclei of at least 2 different targets. Its success hinged on a single, critical maneuver, the firing of a solid rocket motor to blast it free from Earth orbit and onto an interplanetary path. Ground controllers watched the telemetry data stream in, and then they saw the signs of a sudden, violent death. The data showed a sharp, terrifying temperature spike, followed instantly by a total loss of signal. The solid rocket motor had not just failed, it had likely overheated and exploded, shattering the spacecraft into a cloud of tiny, untrackable fragments. The ambitious mission was over in an instant, its entire scientific promise vaporized. The resulting debris field was so dispersed that it simply vanished, becoming an invisible, permanent smear in orbit around our planet. How could a mission designed to survive the hazards of deep space be destroyed by its very first step? The subsequent investigation uncovered a brutal lesson in thermal physics. The design of the propulsion system had insufficient margins to handle the extreme heat generated during the burn. Essentially, the engine cooked itself and the spacecraft along with it. There had not been enough testing to simulate these exact, punishing conditions. Contour was a stark reminder that the most complex and daring journey can be undone by a single, underestimated physical force. It forces us to ask a difficult question: how do you balance the incredible ambition of visiting multiple worlds with the raw, explosive danger of the propulsion needed to get there? The void between planets is perilous, but sometimes the greatest threat is the controlled explosion you light yourself. Even the most perfect journey through space can be shattered on the threshold of home. The Genesis spacecraft was a scientific jewel, a collector of the sun itself. For over 2 years, it floated at a special point in space, extending delicate wafers to capture pristine particles of the solar wind, material unchanged since the birth of our solar system. Its mission was a spectacular success, and the plan for its return was equally daring. A sample return capsule carrying these priceless cosmic samples would plunge into Earth's atmosphere over Utah. A helicopter crew was poised to snatch its parachute from mid-air in a dramatic aerial capture, preventing any contamination from touching the ground. But as the capsule fell towards the waiting recovery team, nothing happened. The parachutes never opened. The Genesis capsule became a 300-pound meteorite, slamming into the desert floor at nearly 200 miles per hour, embedding itself in the soil and cracking open like an egg. The mission that had flawlessly navigated the void for millions of miles had failed in the final seconds. How could this happen? The answer was devastating in its simplicity. Inside the capsule were tiny devices called G-switches, designed to sense the brutal deceleration of re-entry and trigger the parachute deployment sequence. These switches, no more complex than the clicker in a ballpoint pen, had been installed backwards. The very sensors meant to save the mission were rendered completely blind, unable to feel the force they were built to detect. The result was a catastrophic success. The capsule had survived re-entry, but its violent impact ruptured the delicate collection canister. Many of the pristine solar wafers were shattered, their surfaces contaminated by Utah desert dirt. Scientists faced a monumental forensic puzzle, picking through the wreckage to salvage science from the debris. In a heroic effort, they painstakingly cleaned the fragments and managed to analyze enough pure material to still achieve most of the mission's core goals. They confirmed, for instance, that the Sun has a different isotopic composition than the inner planets, a fundamental discovery about our cosmic neighborhood. But the Genesis crash remains a haunting lesson. It was not a failure of advanced physics or complex engineering, but of a basic, reversible human error during assembly. A single component, installed incorrectly, had turned a billion-dollar triumph into a heart-stopping near disaster. It forces us to confront a difficult truth that after conquering the immense challenges of space, the final and most unforgiving obstacle can be a mistake so small you could hold it in your hand. A spacecraft's own safety net can sometimes become the trap that seals its fate. The Stereo mission was a pair of brilliant solar sentinels, two nearly identical observatories named Stereo ahead and Stereo behind. Their orbits were a masterstroke of celestial choreography, placing one ahead of Earth and one behind, slowly drifting apart to give humanity its first ever three-dimensional view of the Sun. This stereo vision allowed scientists to see solar storms not as flat images, but as vast, evolving structures, tracking them from their birth on the solar surface all the way to Earth. But in October 2014, one half of that perfect pair went silent. Stereo B was not struck by a meteor or felled by a power failure. It vanished because of a planned test, a routine exercise of its command loss timer. This was a built-in safety feature, a reset switch designed to kick in if the spacecraft ever went 72 hours without hearing from Earth. The test was meant to prove this system worked. Instead, it triggered a cascade of failures. The reset itself appears to have caused a momentary glitch in the spacecraft's inertial measurement unit, its internal sense of balance. That tiny stumble was enough. Stereo B lost its orientation, its stabilizing gyros struggling to correct a problem they could not fully understand. As it began to tumble, its main antenna drifted away from its precise lock on our planet. The very system designed to save it had instead marooned it, a functional observatory now spinning uncontrollably, its calls for help broadcast into an empty sector of the sky. For 22 months, NASA's Deep Space Network listened, casting a net of radio waves into the void, hoping for an echo. Then, in August 2016, a miracle, a faint, fluctuating signal was found. Stereo B was alive, but the brief contact confirmed the worst fears. The spacecraft was caught in a slow, steady spin, its power levels surging and fading as its solar panels rotated in and out of sunlight. Most critically, it could not stabilize itself enough to point its high-gain antenna back at Earth. The team had a fleeting window to send recovery commands, but the spacecraft's disoriented state and the immense communication delay made it like trying to perform brain surgery with a 10-hour lag. The signal faded, and this time it did not return. the loss of Stereo B was a slow burn mystery, a lesson in the perils of autonomy. How do you program a machine to save itself from every possible contingency without accidentally programming its own demise? Its twin, Stereo A, continues its lonely vigil, a testament to the mission's original design and a constant reminder of the delicate partner it lost to a well-intentioned command. The universe's most violent explosions were supposed to meet their match in Hitomi. This Japanese X-ray observatory, whose very name meant pupil of the eye, was designed to be humanity's sharpest vision into the cosmic furnaces of black holes and supernova remnants. For 37 days, it performed flawlessly, a testament to international collaboration and cutting-edge engineering. Then, in a matter of hours, it tore itself to pieces. The catastrophe began with a single mistaken thought. Hitomi's attitude control system, its internal sense of balance, developed a software delusion. It became convinced the spacecraft was spinning when it was perfectly still. Acting on this false panic, it commanded its reaction control thrusters to fire, to halt a spin that was not there. The thrusters ignited, and in doing so, they shoved the observatory into an actual, violent rotation. Once the real spin began, the system's confusion only deepened. It misread the data, seeing the frantic tumbling as proof it needed to fire the thrusters even more. This created a vicious, self-reinforcing loop, a death spiral commanded by its own flawed logic. The spacecraft was soon whirling so fast that its solar arrays, not built for such stress, ripped away from the main body. The observatory shattered, creating a cloud of glittering debris that was tracked by radar from the ground. One moment, a $250 million window into the high-energy universe, the next, an expanding field of silent shrapnel. The investigation revealed a chain of failures, a perfect storm of software bugs and human misinterpretation. Ground controllers had received early telemetry warning of the growing problem, but by the time they diagnosed the bizarre data, it was too late to send a command that could break the fatal cycle. How could such a sophisticated machine turn its own safety systems into weapons of self-destruction? Hitomi's demise is a chilling lesson in the absolute necessity of fail-safes within fail-safes. It forces engineers to ask not just what a system is supposed to do, but what catastrophic action it might take if it ever, even for a moment, loses its mind. The silence that greeted the returning Soyuz 11 capsule was profoundly wrong. On the surface, everything seemed perfect. The spacecraft had completed a flawless automated re-entry and landing on the Kazakh steppe in June 1971. Recovery crews rushed to the site, their cheers dying in their throats as they opened the hatch. Inside, they found the three cosmonauts, Georgy Dobrovolsky, Viktor Patsayev, and Vladislav Volkov, seated peacefully in their couches, unmoving. They had perished during the final moments of their journey home. The investigation uncovered a brutal, simple flaw. A pressure equalization valve designed to open after landing to equalize the cabin pressure with the outside air had been jolted open prematurely during the separation of the spacecraft's modules. At an altitude of over 168 kilometers, the cabin depressurized in less than 60 seconds. The crew, not wearing pressure suits, had no chance. This was not the loss of a machine, but of human beings, a tragedy that echoed the silent disappearances of robotic probes with a terrible, personal clarity. The subsequent redesign of all Soyuz spacecraft was swift and uncompromising. Cosmonauts would now be required to wear pressurized suits during the most dangerous phases of flight, launch, and re-entry. The very philosophy of engineering shifted, reinforcing a core principle that would become gospel for both human and robotic missions: you must design for failure. Every system, every valve, every line of code had to be examined through the lens of what could go wrong. The ghost of Soyuz 11 forced engineers to ask a new, more urgent question of their robotic creations. If a single valve could claim 3 lives, what catastrophic chain of events could a single faulty transistor or a miswritten line of software initiate in a probe millions of miles away? The answer was to build in layers of redundancy, to assume that any component could fail at the worst possible moment, and to have a backup plan ready. This human tragedy became a foundational lesson for the entire spacefaring world, a stark reminder that the void is utterly indifferent to the distinction between metal and flesh. It forged a direct link between the safety of astronauts and the resilience of robots, ensuring that the hard-won knowledge from human spaceflight would make our silent mechanical emissaries just a little bit tougher, a little more likely to phone home. A slow, creeping death is sometimes more haunting than a sudden explosion. The Soviet Zond 2 probe, launched toward Mars in 1964, did not vanish in a single dramatic moment. It was a ghost in the making, a mission that bled out from 1,000 small wounds across the millions of miles of its journey. This was not a case of one catastrophic failure, but a cascade of technical ailments that slowly strangled the spacecraft. It was equipped with experimental plasma engines, a bold innovation for its time, but that cutting-edge technology could not save it from more mundane flaws. First, one of its 2 vital solar panels refused to unfold. This single malfunction instantly halved the probe's power supply, a devastating blow from which it would never recover. Then, one of its 2 transmitters failed, severing a critical line of communication with its creators on Earth. Zond 2 was now both starved and mute, a wounded machine limping blindly toward its target. Ground controllers fought a losing battle for months, trying to coax life back into their failing creation, but the silence from deep space only grew deeper. Eventually, all contact was lost. The spacecraft is presumed to have sailed silently past the Red Planet, a derelict ship with no one to witness its passage. Its slow demise taught a brutal lesson about the fragility of early interplanetary ambition. A mission could be lost not by a single grand error, but by the cumulative weight of multiple smaller breakdowns. Without sufficient backups for its power and communication, Zond 2 had no margin for error. Its fate asks us a difficult question: how many small things have to go wrong before a billion-mile journey is rendered utterly pointless? This death by 1,000 cuts revealed that the void between planets is not just a place of instant catastrophe, but a realm where patience itself is a weapon, slowly picking apart any machine that is not built to endure. Their silence was not a sudden severance, but a slow and dignified retirement. Perched on the frigid plains of Mars, the Viking landers were designed to last for 90 days. Instead, they became permanent residents, their mechanical hearts beating for years as they transformed from mere machines into our first true outpost on another world. Viking 1 transmitted data for over 6 years, its twin for nearly 4, each day a gift stolen from the harsh Martian environment. They were not just collecting soil samples and weather data, they were answering the most profound question we could ask: are we alone? Their biology experiments, the only dedicated life detection tests ever sent to Mars, yielded tantalizing but ultimately ambiguous results, a puzzle that scientists still debate today. They felt the rumble of Mars quakes, watched frost form on the red rocks, and chronicled the shifting seasons of an alien world. This was not a failure, but a triumph stretched to its absolute limit. Their end came not from a single disaster, but from the slow, inevitable accumulation of age and attrition. For Viking 2, the end was likely a power failure, its batteries finally succumbing to the endless cycle of freezing and thawing. or perhaps a thick layer of fine Martian dust slowly smothering its solar panels, starving it of energy. Viking 1's finale was more poignant, a death by 1,000 lines of code. A human operator on Earth uploaded a routine command to adjust its antenna, but the instruction contained a subtle error. It directed the lander to point its communications dish in a way that permanently broke its ability to lock onto Earth. The final command did not come from Mars, but from our own planet, a gentle, accidental euthanasia for a faithful servant. Both landers now sit in perfect silence, their missions complete, their final states forever a mystery. Are they merely sleeping under a blanket of dust, or are they slowly being scoured away by Martian winds? Their gradual fade challenges the very idea of a lost voyage. Can a mission that succeeded so spectacularly, that answered its primary questions and then lingered for years of bonus science, ever truly be considered lost? Or do these quiet monuments represent a different kind of completion, a story that has been fully told, even if the final page was turned for us by the unfeeling hand of another world? Phobos-Grunt was a ghost before its journey even truly started. In November 2011, this Russian spacecraft, the most ambitious interplanetary mission the nation had attempted in decades, launched perfectly from Earth. It achieved a stable parking orbit, a momentary pause before the main event. Then, nothing happened. The crucial engine burn that would have flung it on a trajectory toward Mars and its moon Phobos never occurred. The spacecraft simply went silent, stranded in a useless loop around its home planet. For 2 months, it was a visible tomb in the sky, a constant, agonizing reminder of failure as teams from the European Space Agency and a global network of amateur radio operators tried desperately to hack into its systems. They were shouting commands at a machine that could not or would not hear them. The investigation into the catastrophe pointed to a flaw that was both simple and deeply systemic. The spacecraft's onboard computer, the brain of this incredibly complex machine, was not adequately hardened against space radiation. Flying through the Van Allen belts, those zones of intense radiation surrounding Earth, the computer experienced a single, random glitch. It reset itself, wiping clean the programmed commands for the engine ignition. With no one to manually restart the sequence from millions of miles away, the mission was stillborn. Phobos-Grunt was not just a probe, it was a Russian phoenix meant to rise from the ashes of earlier Martian failures. Its goals were almost unimaginably bold. It was designed to land on the bizarre, potato-shaped moon Phobos, a world with gravity so weak you could throw a baseball into orbit. There, it would scoop up a sample of soil, launch that sample back into space, and guide it on a multi-year return voyage to Earth. As a secondary passenger, it carried Yinghuo 1, the first ever Chinese Mars orbiter, whose fate was tied irrevocably to its Russian host. This was not one mission, but 3 or 4 separate, incredibly difficult missions stacked into one single, fragile machine. Its failure asked a painful question of every space engineer. Where is the line between ambition and overreach? The complexity was its own enemy. Each new stage, each propulsion burn and delicate maneuver introduced another potential point of catastrophic failure. When the first and most critical step failed, every other brilliant plan locked inside its computers became instantly meaningless. In January 2012, the laws of physics pronounced their final verdict. Phobos-Grunt's orbit decayed, and it tore into the atmosphere over the southern Pacific. Its sophisticated laboratories and the dreams of an international partnership incinerated in a final, brilliant flash. The loss was more than financial. It was a blow to the entire concept of multi-stage sample return missions, proving that the chain of success is only as strong as its very first and most vulnerable link. A new kind of ghost now wanders the lunar plains. In April 2019, the Israeli Beresheet lander, a small, privately funded spacecraft no heavier than a washing machine, had already made history by successfully reaching lunar orbit. It was a triumph of ingenuity, built by the non-profit SpaceIL and Israel Aerospace Industries, aiming to make Israel the fourth nation ever to achieve a soft landing on the moon. It carried a digital time capsule and scientific instruments, a tiny emissary from a new era of space exploration. But during its final automated descent, a single manual command sent from Earth triggered a cascade of catastrophe. An instruction was sent to the spacecraft's inertial measurement unit, its internal gyroscope. This seemingly minor action created a ripple effect, causing the main computer to reset. The reset, in turn, commanded the crucial main engine to shut down completely. Engineers watched in horror as their screens showed the lander, which should have been slowing, instead accelerating in the moon's gravity. They fought to restart the engine, and for a few agonizing moments they succeeded, but it was too late. The spacecraft had already lost too much altitude. Beresheet slammed into the sea of serenity at hundreds of miles per hour, scattering its fragments across the dusty regolith. The investigation revealed a heartbreaking flaw. The system lacked a simple software lockout that would have prevented a ground command from interfering with such a critical system during the landing sequence. It was a failure of foresight, not hardware, a lesson in the absolute need to shield a spacecraft's delicate brain from even well-intentioned interruptions during its most vulnerable moments. This was a modern lost voyage, proving that the perils of landing are no longer confined to government agencies with decades of experience. The entry of private companies with their innovation and appetite for risk brings a new dynamic to the final frontier. Beresheet's story is not one of total loss, however. Its very journey to the moon was a landmark achievement, inspiring a nation and proving that a small team with a big dream could reach another world. Its failure provided a priceless public lesson in systems engineering, one that will undoubtedly make its planned successor, Beresheet 2, a far more resilient machine. The ghost of Beresheet forces us to ask, as commercial ventures set their sights on the moon and beyond, are we entering an age of more frequent, but ultimately more instructive, disappearances? The tension in that Bengaluru control room was a physical presence, thick enough to choke on. India's Vikram lander was just 2.1 kilometers above the lunar surface, the final, delicate phase of its descent to the unexplored South Pole. Then the data stream froze. The green trajectory line on the monitors vanished, replaced by the flat, heart-stopping tone of a lost signal. For 2 agonizing days, engineers at the Indian Space Research Organization sent command after command into the void, hoping for a single beep from their silent explorer. The entire nation held its breath, the fate of the lander and its tiny rover, Pragyan, suspended in a terrible, silent limbo. This was not just a machine, it was the embodiment of a nation's scientific ambition, poised to make India the first country to touch down in this scientifically precious region, a place of eternal shadows where water ice could be locked in the soil. Telemetry from those final seconds told a grimly familiar story. Vikram had begun to deviate from its planned path, and its velocity was just a fraction too high. On the moon, where gravity is 1/6 of Earth's, even a small excess of speed is unforgiving. The lander did not float to a stop, it experienced a hard landing. The official declaration of loss was a devastating blow, a very public stumble on the global stage, but then a glimmer of redemption arrived from another robot orbiting high above. NASA Lunar Reconnaissance Orbiter peered down and spotted Vikram. There it was, intact but clearly tilted, resting on its side on the lunar regolith. It had survived the impact, but the jolt had likely broken its communication antenna, leaving it a functional monument, unable to call home. The investigation pointed to a minor flaw in the braking system's performance, a tiny thrust miscalculation that cascaded into catastrophe during the most critical minutes of the entire mission. How does an agency recover from such a public, nail-biting near miss? The answer lies in what happens after the silence. The data from Vikram's final moments became a priceless, if painful, textbook on lunar descent. Every calculation was refined, every system rechecked, with the ghost of that near success looming over the engineers' shoulders. This very public failure, and the transparent way ISRO handled it, forged a resilience that would prove vital for the next attempt, transforming a moment of heartbreak into the foundational lesson for a future triumph. A veteran comet hunter met its end not in the icy depths of space, but within the confines of its own mind. The Deep Impact spacecraft, famous for its violent and brilliant encounter with comet Tempel 1, spent the next 8 years on a triumphant extended mission. It had fired a copper impactor into the comet's heart, blasting a crater to reveal the primordial secrets within, then sailed on to study other cosmic targets with the versatility of a true robotic explorer. It provided stunning close-up views of Comet Hartley 2 and even repurposed its telescope to aid in the search for alien worlds. This was a spacecraft that had already earned its place in history. Its final undoing was not a dramatic collision, but a mundane software bug. In 2013, a glitch caused the probe's onboard computers to enter a continuous reset loop. Think of a computer that cannot stop restarting itself, trapped in an endless cycle of booting up and crashing. With each reset, the spacecraft failed to execute the most basic commands to maintain its orientation. Its thrusters remained silent, its antennas drifted away from Earth, and its solar panels slowly turned from the sun. Starved of power, its batteries drained into nothingness. Ground teams raced against time, broadcasting software patches into the void, hoping to break the cycle, but the spacecraft was no longer listening. It was a prisoner inside its own malfunctioning brain. How do you plan for the slow decay of a machine's logic over years of service? Deep Impact's quiet fade is a stark lesson in the long-term risks of extended missions. The very software that gives a probe its intelligence can, with one unpredictable flaw, become the cage that seals it in permanent silence. This celebrated explorer, which had survived the hazardous environment of a comet's nucleus, was ultimately defeated by a problem you might encounter with an old home computer, a ghost ship now drifting forever around the sun, a monument to its own past glory and the fragile nature of digital immortality. A ghost from a proven success now wanders in an official silence. The service module from China's Chang'e 5T1 mission completed its headline task with flawless precision, looping around the moon and sending a test capsule screaming back to Earth in 2014. This was a critical rehearsal for future lunar sample returns, proving the ability to survive a blistering high-speed re-entry, but the story did not end there. With its main job done and plenty of fuel remaining, the sturdy service module was given a second act. It was commanded to fly onward, away from the Earth-Moon system, to a distant and stable gravitational parking spot known as the Earth-Sun Lagrange Point 2. This location, 1,000,000 miles from Earth in the opposite direction of the Sun, is a perfect vantage point for astronomy and a test of a spacecraft's ability to hold a steady position. The Chinese Space Agency confirmed the module's successful arrival at this lonely outpost, and then public updates ceased entirely. No fanfare marked the end of its mission, no official declaration of its decommissioning. It simply vanished from the public tracking logs and faded from official discussion. So what became of it? the possibilities are as intriguing as they are unresolved. It might still be there, a silent sentinel holding its position long after its planned lifespan, its instruments dark and its fuel depleted. A system's failure could have crippled it, turning a functional machine into a derelict. Or, most tantalizingly, it could have been secretly maneuvered to another location, repurposed for a new, unannounced objective in the cislunar void. This uncertainty creates a very modern kind of mystery. It is not the loud, catastrophic failure of a Mars lander or the explosive end of a rocket, but a quiet, bureaucratic disappearance. The Chang'e 5T1 service module is a ghost from a mission that already succeeded, a tool that was used and then put away without anyone outside the control room being told where. Its unresolved fate reflects the increasingly complex and sometimes opaque nature of 21st century spaceflight, where a spacecraft's final chapter is not always written for public consumption. How many other capable machines are still out there, their ultimate purpose and final resting place known only to a handful of engineers? Its sail was a vast, shimmering square of silver thinner than a human hair, catching starlight and the faint, constant push of the sun itself. The Japanese Ikaros spacecraft was not a probe in the traditional sense. It was a vessel, the first to successfully sail the ocean of space using sunlight for propulsion. After its triumphant flyby of Venus in 2010, where it proved this revolutionary technology worked, its primary mission was complete. It had done everything it was built to do. For months afterward, it continued to phone home, a bonus period of data collection as it drifted through the inner solar system. But eventually, as its power waned or a critical system finally succumbed to the harsh environment, the transmission stopped. This was not a catastrophic failure or a sudden silence born of error. It was the planned, graceful conclusion to a demonstration, a ship whose engines were the universe itself being allowed to sail on. Ikaros is likely still out there, its sail perhaps still deployed, a silent, shining kite drifting on the solar wind. It represents a different kind of ghost, one that achieved immortality through success rather than tragedy. How do we categorize a mission that was intentionally left to the void after fulfilling its promise? The story of Ikaros blurs the line completely, transforming a lost vessel into a permanent monument, a testament to human ingenuity that is still sailing, even if we can no longer hear its song. A ghost and its living partner now share an orbit around the red planet. The ExoMars Trace gas orbiter circles Mars as a resounding scientific success, its sensors meticulously sniffing the thin atmosphere for elusive gases like methane. Every day it fulfills its primary mission, yet its very presence is a constant, silent memorial to the lander that fell. Schiaparelli's impact scar is a permanent feature on the world below, while its twin, the TGO, sails serenely overhead. This mission embodies a profound duality, a partnership where one half triumphed while the other vanished into the dust. The orbiter's success is undeniable. It acts as a vital communications bridge, relaying the precious data from rovers like Curiosity and Perseverance back to eager scientists on Earth. Its own scientific instruments are unraveling the mysteries of Martian atmospheric chemistry, searching for clues that might hint at past or even present life. But each successful data transmission, each relayed image from the surface, carries a subtle, unspoken echo. It highlights the precise capability that was lost, the dream of a European lander operating independently on Mars. How do you weigh the value of a mission when its outcome is so starkly split? The legacy of ExoMars is not one of pure victory or total defeat, but of a complex, bittersweet reality. The orbiter's enduring, flawless service provides a crucial silver lining, a productive life that continues to justify the entire endeavor. It demonstrates the compartmentalized nature of risk in these grand projects, where the failure of one component does not necessarily spell doom for the whole. The sting of Schiaparelli's loss is mitigated by the TGO's daily contributions, a reminder that in the harsh economy of space exploration, even a tragedy can leave behind a working tool of immense value. They were not meant to be permanent residents of the Moon. The 5 American lunar orbiters of the 1960s were sent with a single, vital purpose: to map our celestial neighbor with a clarity never before seen, and they succeeded beyond all expectation. These photographic scouts captured over 99% of the lunar surface, their high-resolution film revealing boulders the size of cars and slopes that could tip a spacecraft. Their images were the literal roadmaps for the Apollo program, the reason Neil Armstrong and Buzz Aldrin knew where to set down. Yet for all their success, their final act was one of deliberate destruction. With their film canisters ejected and their data safely transmitted to Earth, each orbiter was commanded to fire its engine one last time, not to come home, but to dive into the gray dust below. These were not accidents or failures, but calculated sacrifices. A functioning satellite left in orbit could become a navigational hazard for the crewed missions soon to follow, a tiny moon of deadly debris. So they were guided to their ends, their transmissions cutting out abruptly upon impact. The irony is profound. We know the general vicinity of their final resting places, but the precise craters they carved into the regolith have been lost to time, their scattered metal bones now buried and silent. These were ghosts by design, machines that served their purpose flawlessly, and were then intentionally vanished to clear the way for humanity's next giant leap. Where do we draw the line between a lost spacecraft and one that is honorably retired? The lunar orbiters force us to confront a difficult truth, that sometimes the greatest service a machine can render is to remove itself forever from the sky, becoming a permanent part of the world it helped us conquer. That single piece of history, the Apollo 10 lunar module named Snoopy, is still out there. It was not a failure, but a deliberate castaway. After its crew, Tom Stafford, Gene Cernan, and John Young, completed their flawless dress rehearsal for the moon landing, they faced a final, strange procedure. The spidery ascent stage, its job done, had to be disposed of. With the astronauts safely back in the command module Charlie Brown, the hatch was closed for the last time. They fired the small explosive bolts, and Snoopy drifted away into the blackness. Then, ground controllers sent the command to fire its engine, not to bring it home, but to burn all its remaining fuel, sending it careening onto a path around the sun. This was not an act of carelessness. It was a calculated act of celestial housekeeping, ensuring this empty ship would never become a navigational hazard for the critical Apollo 11 mission just 2 months later. Snoopy was transformed from a vital spacecraft into a permanent ghost, a piece of 1969 engineering forever sealed and silent. For decades, its location was a matter of vague estimation, a rough map drawn by the laws of orbital mechanics. But in 2019, a group of dedicated amateur astronomers decided to try the impossible, to find a needle in the cosmic haystack. They are using some of the most powerful telescopes on Earth to scan the predicted regions of space where Snoopy might be. The challenge is almost unimaginable. They are searching for an object perhaps just a few meters across, millions of miles away, reflecting only the faintest glint of sunlight. It is a treasure hunt on a solar system scale, driven by the pure passion to reclaim a relic of our greatest adventure. Snoopy's story connects the silent tragedies of robotic probes to the triumphant saga of human exploration. It is a tangible link, a physical piece of the Apollo program that is not in a museum but is still traveling, a silent witness to the courage it took to send people to the moon. This raises a profound question: what other artifacts of our ambition are adrift in the void? How many other spacecraft, having served their purpose, were cast into solar orbits to become permanent, untracked monuments? The search for Snoopy is more than an astronomical challenge. It is a quest to touch a piece of our own history, a ghost that calls back to the moment we first reached for another world. Their silent journeys began with a race against the sun itself. The Helios A and B probes, a partnership between West Germany and the United States, were built for a single, audacious purpose: to fly closer to our star than any machine before them. Launched in the mid-1970s, these twin spacecraft were engineering marvels, shielded by a sun umbrella and spinning like tops to survive a hellish environment. They plunged into the inner solar system, diving inside the orbit of Mercury to feel the full, blistering fury of the solar wind. For years, they transmitted a torrent of data, measuring the sun's magnetic field, counting cosmic rays, and fundamentally changing our understanding of the star that gives us life. In the process, they achieved a record that still stands today, becoming the fastest human-made objects in history, screaming through space at nearly 250,000 kilometers per hour. Yet their story does not end in a fiery plunge or a sudden, tragic silence. Their final chapter was one of quiet, deliberate retirement. After their primary missions and a long, productive extended phase, their systems began to show the inevitable wear of age and radiation. The scientific return began to diminish, and the difficult decision was made to terminate communication. The last signals were sent not from a failing machine, but from a veteran explorer being respectfully put to rest. Their transmitters were switched off for the last time, and a profound, planned silence fell. The Helios probes were not lost, they were released. They continue on their eternal, elliptical paths around the sun, their instruments dormant, their voices stilled, but their hardened shells perfectly intact. They are ghost ships of a different kind, not victims of catastrophe but honored retirees. Their voyages complete, they form a hidden fleet of past explorers, countless other retired spacecraft from nations around the world, all silently tracing their endless circles around the gravitational heart of our solar system. How many such monuments to human curiosity are now permanent companions to the sun, their missions accomplished but their physical forms enduring? The legacy of Helios is a powerful reminder that in the vast archive of space, not every silence is a scream of failure. Some are a whisper of a job well done. A ghost the size of a suitcase now circles the sun. The Japanese Procyon spacecraft weighed little more than an average adult, a tiny box of miniaturized ambition launched in 2014 to prove that small and cheap could conquer deep space. Its name stood for Proximate Object Close Flyby with Optical Navigation, a mouthful for a mission with a simple, audacious goal: to test new technologies and then fly by an asteroid. But its revolutionary ion engines, a fuel-efficient propulsion system that emits a faint blue glow, were its greatest innovation and its ultimate undoing. A single valve inside that delicate system failed, a tiny component that acted as a gatekeeper for the propellant. With that gate stuck shut, Procyon could not perform the essential trajectory adjustments needed to steer towards its target. It was a marooned ship stranded in an orbit around the sun that mirrored Earth's, a permanent prisoner of its own failed mechanics. For a while, engineers managed to contact the silent probe, pulling down precious data from its technology demonstrations, a brief whisper from a machine that was already lost. But eventually, even that tenuous link was severed. Its batteries likely drained or another system succumbed to the harsh environment, leaving Procyon to drift in perpetual, uncommunicative silence. This was not a dramatic explosion or a shattering impact, but a slow, systemic suffocation. the failure poses a difficult question for a new era of space exploration. We can build spacecraft smaller and more affordable than ever before, packing incredible capability into a tiny frame. But can these microprobes survive the relentless demands of interplanetary travel? Procyon fate whispers a cautionary tale that scaling down a spacecraft also scales up its vulnerability. A single faulty valve on a billion-dollar flagship might be a redundant component, but on a 65-kilogram micro-spacecraft, that same valve is a single point of catastrophic failure. The void does not care about your budget or your innovative spirit. It only respects resilience. The silent drift of Procyon is a modern monument to this old truth, a reminder that while our ambitions can be miniaturized, the unforgiving nature of space